So we would say in section 6.2 that a set of vectors u1 to up is called an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, if ui dot uj equals 0 when I doesn't equal j. This is important. This isn't hard, but there's some notation here. So let me make sure you're tracking what's going on. So if I want to determine whether these three vectors are orthogonal, we can call the first one u1, the second one u2, and the third one u3. And so what this theorem is telling us is that we need to look at u1.u2. We need to look at u1.u3. And we need to look at u2.u3. Why am I not looking at u1.u1 and u2.u2 and u3.u3? Yeah, from dibs, that would be when I equals I. So this section up here where we have I and j and we say I doesn't equal j is why we make sure that we wouldn't have 1 and 1 and 2 and 2 and 3 and 3. So good call. So if we want to find u1.u2, u1.u2 would be, well, do you guys have it for me? What's u1.u2? I've got -12 plus 21 minus 9, which is a nice friendly 0. So that tells us that u1 is perpendicular to u2. So then we come in for u1.u3. So I've got 6 minus 7 plus 1, which is equal to, again, lots more zeros. Thanks, Gerline, Felix, Tommy, Abed. And then lastly, we want to find u2.u3, -18 minus 3 minus 9, which is, what's important about this? I've got lots of -30s, but what's important about -30? Yeah, from Felix and Megumi. We got our bang equals. So it's bang equals not equal to 0. So what does that tell us about these vectors? It tells us that this is not an orthogonal set. So thanks, Felix, Ryan, Sammy, for that conclusion. All right, well, that was disappointing. Let's try it again and see if it works out better the next time. So in the next case, we're going to do the same thing. Here's our, maybe we'll call them V's this time. Here's our V1, our V2, our V3. You might guess, and you probably would be accurate, that these ones are going to be orthogonal. So we can find, again, v1.v2. So this is saying I equals 1, j equals 2. And we can find v1.v3. And we can find v2.v3. So I've got -3, whoa, 6 minus 3 plus 12. So the first one's 0. Second one, it is 0. And the third one, it's also 0. So they're all 0. We tried every possible combination. So yay, it's an orthogonal set. Pretty easy money. So going back to that definition that we had up above, I hope you now all understand this idea of an orthogonal set. You just try all the combinations. How does it work out? Okay, pretty easy to verify. Let's see if we can do one. Boy, there's a little proof here. 2 minutes left. Let's at least start this proof. I don't know if we'll be able to finish it. So our theorem 4 says if S equal to U1 to UP is an orthogonal set of non-zero vectors in Rn, then S is linearly independent and hence is a basis for the subspace spanned by S. So we want to prove it. So think about what we know about proofs. So first thing we need to do is define our terms. So we could let S equal to U1 to UP be given as above. Now we're trying to show that S is linearly independent. So if we're trying to show it's linearly independent, what are we going to need to do to show that something is linearly independent? So from Alex, something about the homogeneous equation. What about the homogeneous equation? And from Kevin, only the trivial solution. So we need to show that C1U1 plus plus CP UP equals 0 has only the trivial solution. So that is, we've got to show that all the C1s to CPs are equal to 0, right? From Croy, we could show that it's row equivalent to the identity matrix, but the one catch is that it might not be the full identity matrix because there's only P vectors here and we're in Rn. So if P and N were the same, it might be row equivalent to the identity matrix, but it's not necessarily filling out the whole space. So when we pick this up again tomorrow, we'll do a little clever trick to show how to show that all the C1s to CPs are equal to 0. But that can wait. I think you'll all be able to sleep even without having quite proven this theorem. For today, we've made it far enough, right? We know about orthogonality, we know about length, we know about inner products, and we have also introduced this new idea of an orthogonal set, which so far seems like a pretty chill little entity, like just a whole bunch of dot products showing up. So as with all proofs, we started by defining our terms, initializing all our variables for those of you that program. So we let S equal U1 to UP, and we say that it's given as above. And then we want to see where we're going. So we wrote that we need to show, or NTS, that C1 U1 plus plus CP UP is equal to 0 has only the trivial solution. So this idea that it has only the trivial solution, equals 0 has only the trivial solution, that's what ties to this idea of linear independence. Okay. So let's see how it works. So let's solve 0 equal to C1 U1 plus plus CP UP. And what we're trying to figure out is what are all of those values for C1 to CP. So let's consider UI, so the ith U vector dotted with 0. I dotted it on the left. Wrong thing. Come on. So I'm dotting it on the left. And then if I dot it on the left, I've got to also dot it on the right. And again, don't miss that dot product that's there. Okay. And this is an I. Okay. So you might say, well, which I are we focusing in on? We're going to do this for all the I's. This would be for I equal to 1, 2, all the way to P. So if I take that UI and I dot it with that linear combination, then I can simply distribute on the right side. So what's going to be UI dotted with 0? That should be pretty straightforward. And is it, so I got 0 from 3 or 4 of you, is that 0 scalar or 0 vector? And from Twee and Dibs, it's the 0 scalar. So I've got 0 equals, and then we can distribute the UI to all the individual terms. So I would have UI dotted with C1 U1 plus dot 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 plus UI dotted with CP UP. Okay. Now, tell me about UI. The C can move in and out, right? So this little C1 could move out front. That's not a problem. And the CP could move out front. So tell me about UI dotted with U1 and UI dotted with U2 and UI dotted with U3. So UI dotted with all those other U's is going to be equal to what? And the key here is to remember, maybe you're remember that this is an orthogonal set. So it's an orthogonal set, as Evan said, the UI dotted with U1 is going to be 0 since those are orthogonal, and UI dotted with U2 is going to be 0 since they're orthogonal, and UI is going to be dotted with U3 is going to be 0 since they're orthogonal. It's going to be 0 every single time except for which one? There's one case when it won't be 0. Yeah, from Ahmed, from Felix, when you have UI dotted with itself, when you're using the same U. So this works out to be telling us that we have 0, and we've got a whole bunch of zeros. Plus 0, and then at some point we're going to have a CI UI dotted with UI, and then we're going to get a whole bunch more zeros. So we've got CI UI dot UI equals 0. Cool. Well, all those other terms were 0. Tell me about the value of UI dot UI. Specifically, this one right here is not equal to 0 from Twee. Thank you. So this was not equal to 0. Is it a number, a vector, a matrix, a scalar? What kind of critter is UI dot UI? It's a scalar. Yeah. It's not necessarily 1 because we don't know that these are orthogonal, or sorry, are normal vectors, unit vectors, but we do know that it's not 0. So that tells us that we could find CI by taking 0 divided by UI dot UI, which would be the same thing as 0. So we just showed that CI is equal to 0, and this would be true for I equal to 1 to all the way to P. So what does that tell us? From Dibs, from Felix, from Gerald, who's disconnected, and a few others that need to be let in. Sorry about that, folks. Thank you, Regan, for the note, the reminder. So this tells us that that there's only the trivial solution to the homogeneous equation. Like, remember, you always have the homogeneous equation or solution. The key is that you have only the trivial solution. And so if you have only the trivial solution to the homogeneous equation, what does that tell you about U1 to UP? They are from Kevin, Ryan, Gerline, Felix, Tommy, and Twee. They are linearly independent. Woohoo! So they're linearly independent. Clearly they span. Clearly S, that was the set of vectors, S spans the space. So you have linear independence. Span is kind of obvious. Therefore, S equal to U1 to UP is what? So if it spans and is linearly independent, then it is a basis. So a little definition based on what we just did. So an orthogonal basis for a subspace W is a basis that is also orthogonal. You probably couldn't have figured that out without the name or without the definition. An orthogonal basis is a basis, and it's an orthogonal set. Woohoo! So what we're going to do in this next bit is we're going to talk about what we can do with orthogonal bases, how we can use them. What we aren't going to do in this section is figure out how to find them. So in this section, 6.2, we're going to learn properties of orthogonal sets. In the next section, 6.3.6.4, we're going to learn how to find an orthogonal basis. So again, so far we're just going to be given them. So theorem 5, let U1 to UP be an orthogonal basis for a subspace W of Rn. For each y in W, the weights in the linear combination y equal to C1 U1 plus plus CP UP are given by Cj equal to y dot uj over uj dot uj for all the j's. Can you give me another name here? We have these C1 to CP, and we call them the weights here. What's another word for weights? Yeah, from Evan. These are it's similar. It's not quite the same thing because we might not be filling out the whole space, but at least for the subspace, you could think about weights as being the same thing as the coordinates. With respect to the orthogonal set or the orthogonal basis. Okay, in this particular case. So what we're saying is that you can find those coordinates using this formula where for the CJs. Think back to what we did in chapter 4 when we were learning about coordinates. Remember how we had that change of coordinate matrix, and we had the PB matrix and the PB inverse matrix and the PB to C matrix, and there are all these somewhat complicated matrices that would help us figure out how to represent, how to find the new coordinates with respect to these new bases. Like, I'm hoping you remember that. Here, notice that there's no matrix involved. We can find the coordinates simply by finding this ratio of dot products. Okay, so let's see why this is the case. Okay, so if we want to know why, let's take this equation that we started with, the y equals C1U1 plus dot 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 plus CP UP. And let's dot both sides with UJ. So this would mean we would have UJ dotted with Y equals UJ dotted with C1U1 plus dot 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 plus CP. Okay. Now the left side, UJ dotted with Y, we don't know what that is. But the right side should look pretty similar to what we had in the proof that we were just working through. And so what's going to happen when we take UJ and we dot it with C1U1 plus dot 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 plus CP UP. What's going to happen over here on the right side when we distribute that dot product? From Felix, we're just going to be left with CJ UJ dot UJ. All the other terms are going to be 0 because the U vectors are which kind of basis? It's an orthogonal basis made up of an orthogonal set. So all those other vectors are going to be 0, or all those other dot products are going to be 0. Thank you, Gerald, as well. And so all we're going to be left with is CJ times UJ dot UJ. So we're going to have UJ dot Y equals CJ UJ dotted with UJ. All the other ones are going to go away because of the properties of orthogonal sets. And so our goal here is to solve for this CJ. That's what we're trying to figure out. And so we get that CJ is equal to UJ dotted with Y over UJ dotted with UJ. And note that this is the same thing as Y dotted with UJ. Doesn't matter the order. So this formula we found here is the exact same as the one that's given in the theorem. questions? Very good. So let's just crunch through this. See how this works. So in example 2, I'm given the vector v, 4, -8, -10, 17. It's in the subspace W with orthogonal basis given that we already had worked with. And so I want to express v as a linear combination of the orthogonal basis. And so what I need to do is write v as C1 V1 plus C2 V2 plus C3 V3. Here's my V1, my V2, my V3. Okay. And we need to find those C1, C2, and C3. So if I want to find C1, C1 is going to be V dotted with, oh, let me change from V's to U's. I'm sorry, this is, I want to clean this up so the notation stays consistent for you. So instead of calling this V1, let's call this U1, U2, U3, U1, U2. That'll just make the notation line up a little bit better with what we had before. So V is going to C1 is going to equal V dot U1 over U1 dotted with U1. So if I want to figure this out, the first thing, in order to find my numerator, I'm going to dot the V vector and the U1 vector. So I'm going to get like 12 plus 16 minus 10 plus 51. And then to find the denominator, I'm just going to take that U1 vector and I'm going to dot it with itself. And I'll get 9 plus 4 plus 1 plus 9. So I think I've got 69 over 23, which is a funny way of writing 3. Yeah, thank you, Gerline. Now, that calculation might have been a little bit of a pain, but notice that no matrices were required, right? You could have used matrices, but you didn't have to use matrices here. So similarly, we could find C2, and C2 works out to be 2. And you could find C3, C3 works out to be -1. I see. From oh, thank you. I think I said 51 and wrote 5. Thank you for the correction there. So altogether, we have that V is equal to 3U1 plus 2U2 minus U3. Questions, comments, corrections? So let's make sure you're tracking the main point so far. So if you have an orthogonal basis, it is super easy, barely an inconvenience, to find coordinates. But this if is a big deal, right? That's if you have it. We don't know how to find it yet. We just know how to find it. We also know how to verify that we've got one, but we don't know how to find it. And so we've got to start working our way toward how we would find an orthogonal basis. So the next step in that process of finding an orthogonal basis is understanding the idea of an orthogonal projection. This idea of an orthogonal projection gets hit in Calc 3. I think it comes up in physics and engineering a whole bunch. And it shows up here again in linear algebra. So imagine that you're given a vector y. So we're going to say you're given this y vector. Okay, so I'm given this y vector. I'm also given the space W. Okay. And so my question is, how much of y is within W? So I want to find the projection of y onto W, and I also want to find the part that's perpendicular. So I'm going to break y into two parts. Okay. So I have the, it's hard to read. I have the part of y that's in W, and we'll call this our projection of y into the subspace W, and we'll give it the name y hat. And then we also have this other part of y perpendicular to W, or in W perp, and so this part will be z, and it will be equal to y minus, let me get my colors right, equal to y minus the part of y that's in the space. Okay. So it's all the stuff that's not within the space. So far, so good on the picture. My picture is in 3D, but there's nothing about the derivation that we're doing that requires things to be in 3 dimensions. So these concepts apply more broadly. So again, we're saying that y vector that we start with is equal to, you can imagine taking this formula number 1 in the bottom corner, and you could solve for y, and so it's equal to, ooh, I lost a hat. Sorry about that. That's a y hat, the blue y hat. So it's equal to blue y hat plus purple z. So it's equal, so y is made up of the part that's in the subspace plus the part that's perpendicular to the subspace. All right. So this is telling us that our same y is equal to, now I'm going to try to look at that y vector. So here's the y vector on the picture. Ooh, it's hard to read. There's the y vector, and is the y hat vector a unit vector? So is y hat a unit vector? Not necessarily, right? It's just a vector. So let's create a vector that will later on become a unit vector, but at this point it's not going to be a unit vector. So let's create another vector in this thing. Maybe we'll call it u, and we'll say that that u is a vector in W. So I'm going to create this vector here that's in W. Okay, and it's in the same direction as the y prime. And so we could say that our y hat would be the same as that u vector, but it has a different length, right? Maybe the u vector is a unit vector, maybe it's not, but certainly the y vector has a different length. And so we're going to have to multiply that u vector by some alpha to get it to show up and be the same length. So now we can solve for z. So we get that z is equal to the y vector minus alpha u. Where does z live? Which space does the purple z live in? From Dibs, from Felix, it's living in W perp. It's orthogonal to W. Now, we don't like things that are orthogonal to W. We want to get rid of them. So do you know of any creatures out there that you could use to turn all the perpendicular stuff into zero? You know, anything that will turn perpendicular stuff into zero? Yeah, from Gerald and from Felix, the dot product is our friend. Let's see if I can. Ooh, worked. All right. So I can dot both sides with the u vector, which is in W. So we have u dotted with z equals u dotted with y minus alpha u. Sorry, a few too many colors there. So remember that the green U lives in W, the purple Z lives in W perp. So what can you tell me again about this dot product? It's a nice, from Megumi and from Felix, it's a nice 0. And so 0 is going to equal U dot Y minus alpha times U dot U. Or in other words, you could get solve for alpha. So alpha would be equal to I guess I could write it in the other order, y dot u over u dot u. So you might have forgotten what the heck's going on here. Remember that we have, oops, wrong color. We have the projection of y onto w is equal to alpha times u. And now we have alpha is equal to y dot u over u dot u. And so you can now see below the formula that your y hat, your projection of y into the space onto the line L, this here would be the line L, is equal to alpha y dot u over u dot u times u, which would be a vector in the space. So we now have a formula for for taking a vector that's outside of a space and finding its projection into a space. Let's just do, oh, no, we don't have very much examples. So let me see if I can help you understand why this matters. So this matters for two reasons. Okay, reason number one matters is because this is going to be a step on the way to finding or creating an orthogonal basis for ourselves. So that's one reason it matters. The second reason it matters is that projecting into a space is conceptually what's happening in the background of least squares regression. So in least squares regression, you're basically saying, I have something that's not a possible solution, but I'm asking what's the closest possible solution. And the closest possible solution would be one that's a projection into the space. So we're sort of in the middle of a derivation, but again, the reason this matters is because it's helping us to create that orthogonal basis, which in turn is a step towards helping us find a way to do those least squares regressions. We had this formula here that the projection of a vector y onto a line L would be y dot u over u dot u times u, where in this case, the u vector is in the direction of L. So let's do an example which will help that formula make sense. There actually is some truth to the fact that I got inked just for the video. Okay, so in example 3, compute the orthogonal projection of 1, 7 onto the line through negative 4, 2 and through the origin. And then we'll write 1, 7 as a sum of 2 orthogonal vectors. Also, we're going to observe it geometrically. So let's start by trying to draw a picture here. So our line is going to go through negative 4, 2. Negative 4, 2. So that would be something like this. So this is our line L. And then we're going to let our line U be any vector that's on L. So got a suggestion for a vector that's on L or parallel to L? And don't overthink about this. Yeah, from Ahmed, negative 4, 2. You could also do negative 2, 1 or 2, negative 1 or any vector that's on the line. But maybe we'll do the one that's given. So here's our vector U. Here's our line L. And so the question is asking us to find the projection of Y onto the line. So Y is 1, 7. I think here's our Y. And so you can see graphically that there's a projection of Y onto L, and it would be the part of the red that's perpendicular to the green. And so it looks like it's going to be maybe like this part right here. So that looks like our Y hat. Okay. So let's find our formula. So our Y hat, which is equal to the projection of Y onto the line, is equal to, we got to do Y dot U. So over U dot U. And all this times vector U. Let's make sure you're seeing our vectors. So again, what's our U vector? In our case, remember that U is the negative 4, 2, but it could have been something else. Okay. And our Y vector is here. So Y dot U would be 1 times negative 4 or negative 4 plus 7 times 2 is 14 over U dot U, which would be negative 4 times negative 4 or 16 plus 2 times 2 or 4. And then we're going to multiply by U. Or in other words, what is that length? I've got 12 over, no, 10 over 20, which is a half. Thank you. So I've got a half times U, which would be a half times negative 4, 2, or our orange vector at the end of the day is going to be negative 2, 1. Thank you, Gerline and Abid, for helping me with my arithmetic. Questions so far? Okay. Last thing is we could also include the perpendicular component of y. So you could think about y, the red y, as being equal to the orange parallel component plus the perpendicular component, which we're calling z in this case. And so if you want to find purple z will be equal to the red y minus the orange y hat. So this would be, what is that, 1, 7 minus negative 2, 1, which is a funny way of writing purple z equal to, what do we have? 3, 6. Thank you, Kevin. And what's interesting, if you look at the picture, I mean, I was sketching this by hand. I don't have great handwriting. I'm on a tablet. But what's crazy is even literally just eyeballing it, like not even doing anything complicated, notice that my purple came out as 1, 2, 3 to the right, and 1, 2, 3, 4, 5, 6. Like it actually came out where it was supposed to, just based on the eyeball hand sketch test. Croy commented that you could think about the u vector as being one of my basis elements, and that's correct. So we're creating a basis, or trying to understand how to do basis or a projection, and we're working towards an orthonormal basis. Questions about this? Very good. Come on. So example 4 asks us to find the distance from the vector 1, 7. Remember, this was our y vector to the line through negative 4, 2. This is that same line that we had before L, and the 4, 2. This was our u vector. Okay. And so you could think about it, and that vector that we found, the y hat, is the closest point on the line through u to y. And I'll say point in quotes, because we ask, is it a vector? Is it a point? How do you want to think about it? But it's the closest point on the line line L through U to Y. So if we're trying to find the distance from Y to U, we've got to basically ask the distance between y and y hat. Oh, I think I did my colors backwards. From y to y hat. Okay. And that would be like the norm or the magnitude of y minus y hat. Okay. Do we have another name for y minus y hat? Yeah, from Felix. That's our z. So we need the magnitude. Oops. We need the magnitude of z, which in our case would simply be square root of 6 squared, or 36, plus 3 squared, or 9, or square root of 45. Let me backtrack a little bit in the notes. So there's the two pictures together. Questions? Very good. So notice that orthogonal projection formula that we just had matches the weights of the orthogonal basis terms in Theorem 5. And I'm trying to remember which one was Theorem 5. That's a couple days ago. Theorem 5 was the one that gave us the formula for the weights. So notice that the orthogonal projection formula matches the weights of the orthogonal basis terms in Theorem 5. So Theorem 5 decomposes a vector into a sum of orthogonal projections onto one-dimensional subspaces or lines. So in R2, if we have an orthogonal basis U1 and U2, then any y in R2 can be written as y dot U1 over U1 dot U1 times U1 plus y dot U2 over U2 dot U2 times U2. If you compare back to Theorem 5, which was a long time ago, this is your C1 and this is your C2. Let's scroll back so you can just remember what I'm talking about. Right here. Here was the Theorem 5. So it's saying that y was equal to C1 U1 plus dot 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 plus CP UP, where those U1 to UP are an orthogonal basis. And then our formulas for those weights was the y dot uj over uj dot uj. Yeah, so this, I hope this does connect back into physics and to other places. Okay. Back in the present. All right, so in our R2 world, we're saying that if we have this vector y here, here's our our y, then we can split that y up into the part that's in the u1 direction, which is this bit right here. That's the amount that's in that u1 direction. And we could split it up into the part of y that's in the u2 direction, which would be like here, perpendicular. Again, we're in the u2 direction. So you can split it up into these orthogonal components. In physics, we use this to decompose a force on an object. And so this is a car being towed. Maybe it's one of my cars. I don't know. So our car is being towed, and you can think about what's happening with, like, in terms of the tensions that are in the cable. So here's your cable at the red Y. And you could think about it that U, the U vector, is the amount that's of force that's going forward, if you will, because the car's being towed along or accelerated along. But then we've also got to counteract gravity. And so we've got this normal component that we got to address. And so, again, we're thinking about it in terms of breaking a force into its orthogonal components. Good. Questions? Cool. So a set of vectors u1 to up is called an orthonormal set. If it is an orthogonal set of unit vectors. If W is spanned by this set, then the set is an orthonormal basis. Okay. The simplest orthonormal basis that you've seen for Rn that we played with are our standard basis vectors E1, E2, all the way up to En. Remember, like, that E2 would be 0, 1, 0, 0, 0 for as many components as you have. Yeah, so remember what's the difference between orthonormal and orthogonal? Like an orthonormal set and an orthogonal set. They're similar, but not quite the same thing. What's the difference? Yeah, from Andrew, they're length 1. From Megumi, the orthonormal uses unit vectors. Exactly. So as soon as you have the normal in there, then you're talking about unit vectors. Good, good, good. Another like a orthonormal basis that you have used in the past. So in Calc 3, in Math 163, you had the tangential, normal, and binormal vectors, or the T and B frame. That was an example of an orthonormal basis for R3 that could do some weird things. So that'd be another example from your past. Notice that if you took a subset of these vectors, it would also be orthonormal. It just wouldn't necessarily be a basis. They would still be linearly independent. They just might not span the space. So let's mess around a little bit to see how it all looks. So determine whether the set of vectors is orthonormal. Is it an orthonormal basis for R3? This is not a very exciting question. Notice we got to do two things, but on 3 vectors. We got to check their length, and we got to check whether they're perpendicular. So maybe let's start with their length. And so if I looked at this first vector, maybe I'll call this one U1. So the magnitude of U1 would be, what are you going to have? 1 over 10 plus 9 over 20 plus 9 over 20, all under the root, which is a pretty funny way of writing writing 1. Thank you. How about for the green U2? Can you see it? Do you see that they're all going to be 1? Does that work? So you got they're 1 and 1. So they're all the right length. We don't know if they're orthogonal. So now comes the fun part. And by fun, I just mean not very fun, just because it's a lot of writing. So now we got to check, are they orthogonal? What's our best tool for determining if vectors are orthogonal? Yeah, from Croy, from Felix, from Mahi, from lots of you, the dot product is our friend in this case. So we can look at U1 dotted with U2. And so it looks like you're going to get 3 over 10 minus 3 over 20 minus 3 over 20, which is a funny way of writing happy 0, right? And then we can do U1 dotted with U3 and U2 dotted with U3. And good news, it's going to work out. They're going to be 0. So since this tells us that they are orthogonal, so yes, they're orthogonal. So if you back up and you think about what we've done, we've said, yes, they're unit vectors. So you're like, oops, that didn't work. So we got unit vectors. They're orthogonal. So that tells us that, sure enough, we've got an orthonormal basis. It's an orthonormal set, but notice you're in R3. So since you're in R3 and it's an orthonormal set, this would be an orthonormal basis because there's enough of them. Questions? Yeah, it's an orthogonal basis, but it's an orthogonal basis of unit vectors. So it's even better than an orthogonal basis. This is like a superpowered basis. All right, so let's look at theorem 6. So quick question before we dive into Theorem 6. It says an M by N matrix U has orthonormal columns if and only if U transpose U equals I. So my question is, are the columns of U, going to form a basis for Rm? Columns of U going to form a basis for Rm. What do you guys think? I guess you can keep thinking, then I get to eat more. Not big into sea salt, but I do like chocolate, dark chocolate. I said I must have made a trip to Fred Meyer. We pretty much go to Fred Meyer every day as a family. But these actually aren't from Fred Meyer. They are courtesy of We Love Kent, where my wife does a lot of volunteering. And so she brought home some surplus. I'm going to ask a good question. Is an orthogonal set necessarily linearly independent? Yes, they're necessarily linearly independent because they're all perpendicular to each other. So there's no way of combining them to be able to get one of the other ones. So you know that they're linearly independent. So that part's good to go. So then the question, they are in Rm, and the question has to do with span. That's exactly right. And so here, notice your vector, your matrix is an M by N matrix. And so it will be a basis for Rm if you happen to have M of these vectors. But if you don't have M of them, imagine that your matrix was 7 by 1, it's not going to span, it's not going to be a basis for R7 in that case. Does that make sense? Excellent. So the proof isn't actually about that. That was just sort of an aside. So let's imagine what our proof is going to look, our vector U is going to look like. So let's let our U matrix look like U1 all the way to UN, where these are the columns. So let's think about what this U transpose U would look like. So we want to look at U transpose U arc. I'm mixing uppercase and lowercase u's. Sorry about that. So U has a whole bunch of columns. So U transpose would have a whole bunch of rows. So this would be our U transpose. And then our U matrix will be U1 to UN. Okay. And then think about how you multiply matrices. So if you want to multiply matrices, you go row dotted with column, row dotted with column. And so if we multiplied all this stuff out, to find the very top entry, we would have the first row in the left matrix times the first column on the right matrix. So you'd have, let me add something here. These are transposes. Sorry about that. So you would have U1 transpose dotted with U1. And then if you wanted to find the next entry over, you'd have the first row times the second column, or U1 transpose dotted with U2, all the way to U1 transpose dotted with UN. And your next, to find the next row, you'd go move down. You'd have U2 transpose dotted with U1, U2 transpose dotted with U2, something like that. And I can't highlight all of these entries because there's too many possibilities, but just so you're seeing at least one of them, this would, for example, be take a risk on the purple. So it'd be like this row dotted with this column would give you that entry right there. Sorry, I try to avoid that horrible fuchsia color or whatever. It's a pretty terrible highlight, but running out of colors. All right, what kind of vectors are U1 to UN? From Felix, they're orthonormal. From Ryan, they're orthonormal. That means they're perpendicular and length 1. So if they're perpendicular and length 1, what can you tell me about that purple 1, 1 element? So it's a vector dotted with itself. So from Felix, it'll equal 1. But if I have a vector dotted with any other vector, it would be, other than itself, it's going to be 0. So sure enough, we have that if our matrix U has orthogonal or orthonormal columns, that would be true if and only if the matrix is transposed times the original matrix would be equal to I. And so We are good to go. And thanks, Twee, Alex, and Juan for that last bit. All right, let's keep going. So this Theorem 7 says a couple things. The top part here says that if you, under the an orthonormal transformation or an orthogonal transformation, it says that length is preserved. It says the length is preserved under the linear transformation. When we have that the dot product between ux and uy is the same as the dot product between x and y, this is telling us that angle is preserved. Under the transformation. And C is sort of a special case of B, but it's saying in particular that perpendicular stuff is preserved. So perpendicularness, orthogonality is preserved. And when I say preserved, I'm saying preserved under the linear transformation, UX. Questions? Okay. I'm going to skip over this example 6. I think it should be pretty obvious what's going to happen here. We're going to figure out what ux is. We're going to figure out what x is. We're going to compare their lengths, and we're going to show that they're equal to each other. So it's just a kind of a little bit of a crunchy thing. And the main point here is, the key point here is, again, that the length is preserved. Okay, so that's what's going on there. So the one other thing I want to hit here at the end of the section is I want to talk briefly about orthogonal matrices. So an orthogonal matrix is a square invertible matrix U such that U inverse equals U transpose. By theorem 6, it has orthonormal columns. So for example, we had that example, that orthonormal basis that we found before. I don't remember exactly what colors we had, but we had something like this. And we showed that all these vectors were length 1. We showed that they were all orthogonal, and there's only 3 components. They formed an orthonormal basis. And so this matrix here, this U, would be an example of an orthogonal matrix. In general, it's tough to find inverses. You got to do all that row reduction stuff. I mean, your calculator is good at it, but it takes a lot of work for your calculator. But if you happen to have an orthogonal matrix, the key is that the inverse of the matrix is just equal to the transpose of the matrix. And certainly, well, inverses are kind of hard to find. Transposes are super easy to find. So we like that.